The first technique we're going to look at is data augmentation. So data augmentation says something kind of like the following. Generating new label data is expensive. If we wanted to go from the 1.2 million ImageNet images to double that, let's say, we would need to go ahead and label 1.2 million more images. That would be expensive. Instead, we're going to try and squeeze more juice out of the images that we have. So if we have an image, which is a cat, and this is a cat that's facing left. Well, we know in the wild, cats are sometimes, we have pictures of cats facing left and cats facing right. So what we can do is programmatically transform this into a mirror image, which is a cat facing right. Okay. So this is our X. Our Y is something that says cat. And here we now have an X prime that we generated that has the same label. So if this is a cat, this is also a cat. And now, if we do that to every one of our training instances, we've now doubled the number of training instances. So if we had 1.2 million ImageNet images, now we have 2.4 million ImageNet images, the originals, and then one swapped. Well, gee, if we can do this, why can't we do other sorts of transformations? So we can flip horizontally. So these are different types of transformations. That's one. What about rotating 90 degrees? Do we see cats, I don't know, like this? Maybe. I mean, certainly sometimes people take photos, right, in portrait or landscape mode, and when you import it into your photo album, it's 90-degree rotated, and you have to rotate it to be right. So it may be that out in the wild, we could definitely see cat images that are rotated 90 degrees to the left or rotated 90 degrees to the right. So we can imagine rotating 90 degrees, plus or minus 90 degrees is a possibility. What about flipping it upside down? Well, in nature, you don't see too many upside down cats. Except, well, I'm not sure if you're aware of the anti-gravity device. So you take a cat, right, and you strap onto the cat a piece of buttered toast. And then you let the cat drop. Well, we know two things. We know one, cats always land feet side down. But we also know something else. We also know toast always lands butter side down. So this causes the cosmos to enter into having this cat with butter toast on it. It just sits on gravity because it can't go down on the toast side, on the butter side, and it can't go down on the feet side. So, in any case, we could certainly have flip horizontally, depending on the situation. If we were looking, for instance, at pictures taken from above of cities, we could easily have rotation in each of the 90 degrees, and it would be just as likely to see it in any of those directions. What else can we do, transformation-wise? Well, we could go ahead and do, what about zooming in? Okay. When we are doing our training, we normally have fixed size images that we're dealing with. So for ResNet, that's often 224 by 224. That's what you feed into your neural network, is a 224 by 224 RGB, red, green, and blue image. but your original image may be larger than that. Okay. So what that could allow us to do, let's forget zooming for a second and just cropping, right? So we can take, if this is our big picture here, so we've got, I don't know, a tree. I'm really not an artist, with a cat in it. We have various possibilities. We could just shrink this image directly to 224 by 224, or we could crop out certain parts of it. Like we could take that part, which happens to be all cat. We could take out a different part, like let's say this one, which happens to be cat head plus whatever that thing is, a flower or a tree, right? So we can go ahead and do quite a few different cropping in here. And then we could also do zooming, right? Maybe we go ahead and just take a small portion of this and expand that out. And it's 224 by 224. So we can do zooming, we could do cropping. What else could we do? We could possibly do rotating for small degrees. Right? So maybe 1 or 2 or 3 degrees clockwise, or 1 or 2 or 3 degrees counterclockwise, which does capture the fact that when one is taking pictures, it's not always completely 100% vertically aligned. Other sorts of augmentation. Well, we could convert to black and white. I'll just say grayscale, actually. So if our images come in both color and black and white, if out in the wild we need to be identifying black and white pictures that we'll be seeing those, then it makes sense that that's one thing we could do. We could take this color one and just convert it to grayscale. We could convert to lower quality, so use different compression settings, because that's certainly something we're going to see out in the wild. Again, we're going to see some photos that have been lossless, right? They're just a let's say an RGB image. A lot of images certainly out there are going to be JPEG, which is a lossy compression protocol, and there are different compression settings you can use, which are high quality all the way down to low quality. Although the low quality gives you low size, so that's another augmentation we can do. So these are some examples of this data augmentation. Now there are a couple of different ways you could do this. Right? One thing you could do is basically just take your training data set and go ahead and apply all sorts of transformations to your original data, making a much larger data set. The problem with that is it takes a lot of time and space, I guess is really what it is. It takes a lot of space, okay? So yes, you only have to do these transformations once, but in some cases, there may be an infinite number of choices of zoom and crop and so on. You can just randomly flip, so you get some subset of them. So instead, what normally happens is as your data set comes in, as you're getting a batch of training instances from your training data set, you'll apply the transforms on the fly. So on the fly, we'll take up an image and we'll say, we'll flip a coin. Maybe 50% of the time we'll transform it and 50% we won't. So 50% of the time we'll just leave it alone, and 50% of the time we'll apply some set of transformations to it and feed it in. And then on the next epoch, as we choose that image, this time it may not get augmented. So as we go through epoch by epoch, we're getting, as far as the training process is concerned here, it's a different data set, right? They're slightly different. We're not getting the same exact set of images because some of them have been augmented. And so again, that helps with the regularization. We're going to tend to generalize better because it appears really that we've seen a lot more training instances than we actually had in the original. Let's think of what else we could do. We could adjust the brightness. We could adjust the color. Again, we don't want to tweak it too much, but you can imagine tweaking it somewhat to match the fact that we might have a camera that has a sensor that registers red more strongly than some other camera, and so therefore an image, two different cameras could see the same image and get different pixels out, right? One might have the reds slightly higher than the other. And so we could go ahead and simulate the fact that we have this variance out in the real world by taking our training data sets and trying to modify the image to see some of that variance, or to generate some of that variance that we see out in the world. So this is a case where we're doing our regularization by augmenting x. So one way to think of it is we're basically changing x as x comes in, randomly each time we have an epoch. An alternative to just changing it randomly would also be every time we come in with an x, we go ahead and generate 5 copies of x. So if we have a batch of 64 images, then every one of those 64, we get the original, plus we get 4 random transformations of it. If we've done this sort of augmentation, the other thing to note is, as well as augmentation during training, we can actually do test time augmentation. So test time augmentation says, hey, when we've got, right, we're actually doing testing, let's say, with the validation data set. Okay, so we've got an image. Maybe it's a tree. Not such a bad tree. All right. So we feed it into our model. So we actually produce f of this x, right? And we're going to get a result back, right? Some probability of whether it's a tree, right? In this case, if we had the image net with 1,000 categories, then we get, for every one of those categories, what's the probability that it's one of these things. What we could do, though, is go ahead and generate, via augmentation, x prime, x double prime, x triple prime, and x quintuple prime, is that what we call it? Feed these all into all into f. And now, right, this gives out y hat. This gives out y hat prime. So now we've got probabilities not only for x, but for x prime and x double prime, triple prime, quadruple prime, and quintuple prime. And now what we can say is, well, if we did these augmentations, right, so maybe what we did is we fed in this tree, and then we'd fed in a tree with x prime happened to be slightly brighter, and x double prime happened to be rotated by a couple degrees, and x triple prime happened to be flipped horizontally, right? And x quadruple prime had some zoom in it, and x quintuple prime had its color adjusted slightly. Well, it may be that the model actually works better on one of those than it did on an original x. And so we can take now our average of y hat prime, all the way to y hat quintuple prime, so that we have a better sense of what the true answer might be. So that's called test time augmentation, abbreviated TTA. So that is a way of improving your validation loss and improving your generalizability at the expense of it's more complicated, because you actually have to call f not just once, but in this case 6 times, whatever number you want.